This lesson is going to talk about the transformation known as the dilation. And if you can't guess it from the picture, a dilation is where we take a figure and we either make her bigger or we make her smaller. Based around a center point, though, there are some technicalities about it. Let's talk about them. So first, let's start with the definition. In a dilation, a figure enlarges or shrinks with respect to a center point to produce a similar figure. Remember, similar means that we are staying the same shape. We're just going to be bigger or smaller depending on a scale factor. So let's talk a little more about this idea of a center point. A center point in a dilation is very different from a center point in, say, a rotation or on a circle. Center point is like right here, and it's the point where everything is coming back towards that center point or it's being radiated out. It just depends on if we're getting bigger or smaller. Notice on this one that my point A and my point A prime in the image are being drawn closer to the center point, and what that means is that my figure is getting smaller as it comes closer to the center. Where just the opposite is true on these nesting dolls. If we look at the small one as our pre-image or our original, everything is getting larger as we move away from that center point, kind of radiating out. So they get bigger when they move away from the center point. Now, another thing that's important to remember is that scale factor is involved. So we're making these smaller and bigger. So let's review what scale factor means. Scale factor is the multiplier that is used to resize the image. So when, for example, if we're going to multiply everything by 2 or double it, that's our scale factor, the number 2. You also need to remember, if you don't write it down for sure, that to find a scale factor, you need to compare the new to the old in a fraction or ratio. So when it comes to transformations, your new is from the image, and you'll get the information from the old from the pre-image. Okay, more about scale factor in a little bit. But scale factor, how do we know when we get bigger and how do we know when we get smaller? Well, it's pretty easy. If the scale factor is bigger than 1, like the number 2 or 5 or 10, then we're going to get an enlargement. If the scale factor, though, is less than 1, like something like a fraction, maybe like 1/2 or 2/3, or a decimal like 0.5 or 0.1, then that's going to cause a reduction to happen. We'll get smaller. Grab your foldable. Let's get this information in there, and then we'll take a look at some specific examples. So the properties of a dilation, here's the first thing. The pre-image, hang on, it's not congruent. That's in there to test you. Is the pre-image the same size and shape as the image? In other words, is it an isometry? It is not. So you need to put a slash through this. This is the symbol for not congruent. And this is the first transformation we've seen that's not an isometry. Make sure you know why it's not an isometry. It would be because it's not the same size. It keeps its shape. Size gets bigger or smaller. Depends on your scale factor, of course. We specify it by the center, and for our problems, the center is going to be the origin. And we also need to use the scale factor, of course, to tell us how big or how small we're going to go. There is one point alone that doesn't move. Any point at the center itself isn't going to move because everything comes towards the center or moves away from the center. So the center is going to stay where it is. But definite changes happen to size. Now, like we've seen before, there are some rules that can help us with dilations to keep some things straight. And in this case, we're going to take a look at what happens when we're centered at the origin, and we need to know a scale factor. So let's review the scale factor one more time, is where we take a length from the image, and we're going to compare it to the pre-image. So in other words, we're going to take the new compared to the old. So what's a length out of the pre-image? Well, the pre-image is here, this smaller blue ABCD. If you want to pick a convenient length, maybe we'll just take AB because it's easy enough to count. That's 3 units long. Now compare that to the A prime, B prime, which is now bigger. How long though? It's 6 units long in the count. So in our scale factor calculation, the image is 6, the pre-image, or what it used to be, is 3. So what's our scale factor? 6 divided by 3 tells me the scale factor is 2. In other words, all my dimensions are doubling for this dilation. All right, the scale factor is 2. Well, let's see what that scale factor did to our points. Looking at the graph, where is A prime? Read it off from the graph here, and you see it's at -2, -2. -2, 2. Where's B prime? Listing that from the graph, reading it here, it looks like 4 and 2. So those are its coordinates. Now, yeah, we're looking for a pattern here. Do you see a pattern taking from the pre-image point to the image point? What's going on with these numbers? And test your pattern if you see it. With our C prime, I see it's located way down here at 6, -2. Does your pattern hold there? How do we get these numbers? Last, where's D prime? Okay, reading that from the graph, that's at -2, 0. Okay, does the pattern hold there? If you see the pattern, then you would see it holds. What I see is that 2 makes a 4 if I double it. So I'm going to times by 2. 1 times 2 gives me 2. 3 times 2 gives me 6. -1 times 2, -2. And that same pattern holds for all of these coordinates. Even the 0, because 0 times 2. 0 times 2 is still 0. So that brings us to a general rule. Why is it all times by 2? Well, yeah, that's our scale factor. So here's our general rule. If you want to get a dilation, you need to take all your coordinates and you need to multiply them. Multiply all coordinates, x's and y's, by your scale factor. Now, fancy schmancy math way to write that in the mapping rule would be this. Take all your x's and your y's, all your coordinates, and transform them by multiplying by the scale factor. Now the scale factor we set up top is k, so it'll be k times x, and then also k times y. Remember, right up here I'm getting my scale factor as k, that's what's coming down there. Let's apply this to a couple of examples and make sure this is making sense. So in this first example, we're going to determine the scale factor. Given a graph, determine the scale factor for it. Now they told us points here, and they also gave us the graph here. So we could do this a couple of ways. We can look at the points and see what happened to them, or we could take some counts off the graph and see what happened to that here. Let's go ahead and start with the original on the graph. And I'm seeing a nice thing to count. I don't want to try those slanted ones, but this nice horizontal line from B to C, that's an easy count. That's 3 units long. How long is it on the image, which is B prime, C prime right here? That's just one little square. So if I want to know my scale factor, I'll abbreviate it like this. The scale factor, it's going to take the 1 unit, and compare it back to what it used to be of a 3. So what's my scale factor? 1/3. Now in question B, we get to do a little review. They want to know how the perimeter of the image compares to the perimeter of the pre-image. How does the perimeter of our little baby pentagon compare to this bigger green pre-image? Well, I don't really want to figure out the perimeter, but remember what we've learned, that the perimeter is a one-dimensional measurement, and that means that I apply the scale factor to it 1 time. So it's just going to be 1 parenthesis, if you will, and 1/3 in it. So it's 1/3 of the original perimeter. What about in part C here, the area? How does the area compare to the pre-image area? Remember, this trick is that area is a 2-dimensional measure, and so I'm going to put 2 parentheses because I'm going to fill them with the scale factor twice. And I get 1/9, 1/9 of the original area. That is a nice review. Now, in example 2, I'm going to take you through the steps to actually graphing a dilation. This time I told you the scale factor is 2.5, so we're going to make everything 2.5 times the original dimension. And yeah, that's going to be an enlargement. We're going to get bigger by 2.5 times on everything. So to start out, your first step is to list out your coordinates. Where's K? It's like 1, 3. Do that for all your points. So take I looks like it's at 3, 3. And then so on. For T, I'm looking at 3, 1. You better check me on this. I usually make a mistake here and there. So E, I'm not going to mess that up. That's 0, 0. Okay, once you have your points listed, then when you want to do the dilation, remember our mapping rule is to just multiply everything by the scale factor. So I'm going to multiply this by 2.5, and I'm going to get my new image point. All right, 1 times 2.5, of course, is 2.5. And multiplying 3 by 2.5 is 7.5, or 7.5. Let's go ahead and plot that. So K prime, let's come out to 2.5 and up to 7.5. And that's going to be located right here. And I'll label it K prime. Now we just repeat the same thing for all these points. So taking I prime through a dilation with a scale factor of 2.5 is multiplying it. I prime. What's 3 times 2.5? Well, I just did it up there, so it's 7.5. And what's 3 times 2.5? Still 7.5. That's not changing. All right, let's put that on our graph. So 7.5 out on X, 7.5 up on Y. And label that one I prime. Okay, halfway there. Now we're going to multiply the t points by 2.5. How many times are we going to multiply by 3? This still is 7.5, and 1 times 2.5 is still 2.5. All right, how hard is this? Graph it. 7.5, 2.5. Are you here? Well, if this could not get any harder, I think it just did. Now we're going to multiply 0 by 2.5. Hope you know your times table. 0 times 2.5 is 0, and 0 times 2.5 is 0. So notice that E prime, that's the only point that didn't go anywhere. This is E prime, and it's still right where it started because why? Because that's the center, and the center doesn't move. All right, you just got to finish it up by drawing in the lines. And there we go. There's a nice expansion, a dilation of the kite. This stuff is awesome. I hope you like it. Try them. We'll see you in class.